Hi everybody, and welcome back as always. Today we are going to be expanding on our earlier discussion of volcanoes. So last time we talked about the basic concepts of volcanism, types of volcanoes, and the wheres, whys, and hows of how they form. With that under our belt, today we are going to be looking at the hazards that these really beautiful but primal landforms can create when they choose to erupt. So to start, we are here in the gorgeous Hood River Valley region of Oregon with the imposing Mount Hood behind us looming over the landscape. So based on what you can see here and what we talked about in our previous discussion, I'd like you to take this opportunity to tell me what kind of volcano you think Mount Hood is. So let's move on to the most violent form of volcanic eruption, the eruptive blast. So this involves a sudden release of immense energy in a single destructive explosion. And these events can be extremely destructive, and the most significant of them become events of historical importance. Places like Santorini in 1600 BCE, Vesuvius in 79 AD, Tambora in 1815, Krakatoa in 1883, St. Helens in 1980, Pinatubo in 1991, and just 2 years ago, the eruption of Hunga Tonga Hunga Ha'apai on the island nation of Tonga, which I'm going to talk about a little bit more here in just a second. This type of eruption most commonly occurs at volcanoes with silica-rich andesitic or rhyolitic magmas. So where would you expect to find that type of volcano? Potentially the most dangerous form of eruptive blast happens when the explosive energy moves laterally down the mountainside instead of up into the air. The explosion's blast wave is then able to pick up and carry tephra and debris, creating this wave of material that can be traveling at nearly the speed of sound. So you can understand how devastating that would be. So let's look at an example. This is Mount St. Helens, as viewed in 1979. It erupted in 1980. So we're looking at Mount St. Helens pre-eruption, but if we go ahead and here it is post-eruption in 1980, and you can see the utter devastation that was created by this blast. So now we're going to go ahead and add an overlay that shows you the extent of the actual blast damage itself. And you can see that this blast actually extended out as far as 19 miles from the volcano. And as an example of the power of this eruptive blast, here's a picture taken shortly after the eruptive event where what was once dense forest is now a series of matchsticks all knocked over in the same direction, pushed over by that blast wave. Now let's talk about something much more current, which is the 2022 eruption of Hunga Tonga Hunga Ha'apai in Tonga. So I'm going to go ahead and bring up a satellite image of that eruption, which you can see here. This was a massive eruption. So it released the equivalent energy of 15 megatons of TNT. So this is a measurement that we usually use for nuclear weapons. And in this case, just to give you a slightly different perspective of it, you're talking about 30 billion pounds of high explosive. That's what would be required to create an explosion of this size. So this is larger than the largest nuclear explosion ever detonated by man. And the pressure wave of this eruption, which you can see here in this short image, circled the Earth multiple times and was actually visually observed in locations on the other side of the world. While immensely powerful, blasts of this scale are thankfully quite rare. But even smaller, more common eruptive events are capable of creating hazards with significant destructive potential. So let's talk about some of those smaller, more common hazards now. Pyroclastic flows are an extremely dangerous phenomenon that occurs during volcanic eruptions. These are fast-moving and incredibly hot mixtures of volcanic gases, debris, and lava fragments that will flow down the slope of a volcano during an eruption, following the natural valleys and river streams that come off the mountain. They can move at upwards of 60 miles an hour down the slope and reach temperatures between 800 and 1,000 degrees Celsius. With speeds and temperatures that high, they are incredibly dangerous to anything in their path. And these form by two primary mechanisms. The first, called fountain collapse, happens when the hot material is lifted up during the eruption into the volcanic column. And as it slowly cools, it becomes denser and eventually starts to fall back to the earth. As it falls, it follows the slope of the volcano, picking up speed and debris as it moves. The second mechanism that can cause a pyroclastic flow is called dome collapse, where an existing lava dome eventually loses its structural integrity and disintegrates, falling down the side of the mountain. So the footage you're seeing here is from Mount Unzen in Japan. In 1991, there were a series of volcanic eruptions on the mountain, and that created a number of pyroclastic flows. This one specifically was created by a large lava dome collapse, and one of the dangers of dome collapse pyroclastic flows is their unpredictable nature. In this situation, there were 43 people still on the mountain when this pyroclastic flow happened, and all of them were unfortunately killed. This includes the notable deaths of two well-known volcanologists, Katja and Maurice Kraft, who were there filming a documentary. If you're interested in the Krafts, there is a really good 2022 documentary called Fire of Love. I highly recommend it, even if it does have a somewhat sad ending. Pyroclastic flows represent the most dangerous and lethal direct hazard from a volcanic eruption. Secondary effects like tsunamis or other things also pose a significant hazard to human life, but when we're talking about direct results of a volcanic eruption, it is pyroclastic flows that are the most dangerous. The term lahar is a Javanese word from the island of Java in Indonesia. It's used to describe a really terrifying phenomenon of a pyroclastic debris flow. Now, we just talked about pyroclastic flows as a mixture of gases and volcanic tephra or other debris. What makes a lahar different is that instead of gases, it's a mixture of water and volcanic debris. The mixture of heat and force from a volcanic eruption is enough to very quickly melt the ice and snow cap on a volcanic mountain. This now liquid water is then going to start flowing down the slopes of the mountain and picking up speed, while also picking up all of the debris, volcanic rocks, trees, etc. as it's moving down the mountain. This mix of volcanic material and water flowing down these steep stream paths and river channels on the sides of the mountain can reach speeds over 200 kilometers an hour. And as it does so, it's entraining more and more material as it goes. So not only is it picking up speed, it's also picking up mass, becoming more and more dangerous, more and more powerful as it moves down the mountain. Eventually, it's strong enough to not only pick up rocks and trees and other debris, but also things like bridges and buildings and livestock and everything else in its path. And it will carry that for a long ways as it slowly loses its energy over the flatter lands outside the mountain until eventually all of that material, and it can be a lot of material, is deposited downstream. While what I just described is the most common type of lahar formation, lahars can also be formed from non-eruptive sources of water. For example, this is Mount Pinatubo in the Philippines, and in 1991 it suffered a series of major eruptions. This was one of the largest eruptions in modern history. Pinatubo was also hit by a typhoon during this eruptive event. This was a massive storm that dropped upwards of 30 inches of rain on the mountain in a single day. To give you an idea, that's the equivalent of a year's worth of rainfall here in Stillwater. So 30 inches of rain is landing on this already unstable landscape of this erupting volcano. We've removed most of the vegetation due to the volcanic eruption. We have unstable new rock that has formed, unstable old rock from the volcano, and this is just a recipe for disaster. So all of this rain falls and carries with it all of this mud and volcanic debris down the mountain. And it carried upwards of 3 cubic kilometers of material. So to give you a slightly different metric, that's 300 million dump trucks worth of mud and debris carried down the mountains and deposited in the lowlands surrounding the mountain. This is a huge event, and Pinatubo's lahars completely changed the landscape around the mountain. Lahars are also a threat closer to home. So here is a map of the lahar threat for Mount Rainier in Washington state. So Mount Rainier, if you're not familiar with it, sits just east of the Seattle metropolitan area, a city with well over 1 million inhabitants. And you can see in the upper left-hand corner here, the city of Tacoma, which is on the southern side of the Seattle metro. And Tacoma itself has about 200,000 people. You'll also notice that Tacoma sits in a large area of orange. Looking at the legend for our map, we can see that that means that we can expect Tacoma to be hit by lahars at a frequency interval of between 100 and 500 years. And geologically, that's a very, very short interval. And so Tacoma, a large city and a large part of an even larger city, lives under a constant threat of significant lahars caused by the active volcano on its doorstep. We've covered a number of potential volcanic hazards here today, and I want you to start thinking about how societies and governments can attempt to mitigate these hazards. Many governments hire or consult with geoscientists or emergency managers to assess, monitor, or mitigate these types of threats. In that vein, for this week's discussion, I want you to talk about mitigating these hazards. In your discussion group, I want you to tell the other members how you would go about protecting people from one of the hazards presented here today. You can choose which one, but remember, please, that millions of people live on or near active and dormant volcanoes. So if your idea is everybody leave, that's not a viable option. It's difficult to get millions of people to just lift up their roots and leave. So be viable and realistic, and as always, be civil and productive. Thank you all for joining me as always, and I will see you next time as we walk the streets of Pompeii and talk about the legendary eruption of Mount Vesuvius.